Hi, welcome to the fifth session on infinite series. Today we are going to focus on decimal expansions available for a real number. From high school onwards, students of mathematics, all students, learn how to find the decimal expansion of a rational number, right? And they learn how to work with that. But very rarely, in fact, to the best of my knowledge, it's never taught, the theoretical basis for decimal expansion, and how to work with them. And this is very much needed because when students go to higher studies, then they encounter two things. One, the use of binary expansion to explain the uncountability of R. And when they go to measure theory or some such thing, then they are introduced the Cantor's Ternary set, middle third set. Then again you use the so-called ternary expansion. And I find students are very uncomfortable with these things. The reason, simple reason is they have not even understood the theory behind the decimal expansion. Once you are understood, you will see the theory behind binary or ternary or for that matter any expansion is actually easy. Yeah. So I'm going to explain. And there's a very, very beautiful application of infinite series with non-negative terms. Surprise how many is somewhat obvious looking facts really need the theory of infinite series to explain properly and to prove rigorously. I hope you like it. Okay, yeah. Let me just share this screen. Yeah. So this is the infinite series 5 decimal expansion date, and there is an article of mine on binary, ternary, and decimal expansions. You can download it from Joel website. Search for binary, ternary, decimal expansions, you will get, and YouTube channel link, and the list of videos from on my channel can be downloaded from the same site as I explained in the other. Okay, that will give you how to watch the videos in order if you want to learn a subject properly. Okay, so let us get started with the decimal expansions. Okay, so let's quickly do. Suppose I have something like half. Okay, so we are going to deal with the decimal expansions of numbers, real numbers, and the interval x, the open interval 0 1. Why? Because as you know, if x is any real number, then you know what is known as the greatest integer, less than or equal to x, right? Therefore if I take x minus x, that is going to be 0. Okay, closed at 0, open. And when this is equal to an integer, then there is nothing to prove, so we can as well, this is an integer, okay, then it's going to be x dot 0. Okay, you know how to write down the decimal expansion, right? Now how do I write that decimal expansion? So I'm going to take three numbers and work all the time with that. 1 by 2, 1 by 3, and I'm actually taking, let us say 751, 0.75. Okay, these are the numbers which are in the open interval 0. Okay, I want to explain the geometry because half and 1/3 you know how to do that, but I want to explain the geometry. Trick is, if you want, think of this as 0 and 1, put 0 for the time being so that you'll understand what is happening. So I have 0 here and 1 here. So for decimal expansion, what do? You dissect, not dissect, I should not say, you break this into, you write it as a disjoint of 10 intervals of each of length 1 by 10. That is very precise, this is 1 by 10. And the next one will be 1 by 10 open, 2 by 10 closed. Sorry, 1 by 10 closed, 2 by 10 open. Next one will be 2 by 10 open, 3 by 10, and so on. And this will be 9 by 10, this will be 10 by 10, right? Now, therefore, if you give me any real number x in the interval, okay, it has to lie in one of the ones uniquely. You understand that? For example, where will half do lie? Half will lie in 5 by 10, 6 by 10. Okay, this is going to be your half, right? Whereas if I take 1/3, where do you think it will lie? It will lie between 1/3 will lie between 3 by 10 and 4 by 10. Yeah, because 1 by 3 is greater than 3 by 10, strictly less than 4 by 10, right? So you know that. And whereas if I take 0.751, where do you think it will lie? It will lie in the interval 7 by 10, 8 by 10. You understand? Therefore, there is a unique thing. This is geometrically, I had located it. Okay. Then what I do? I write the first decimal expansion for x equal to half. The first decimal expansion, I will say, where does it lie? Half lies in 5 by 10, 6 by 10. Then I will write it as 0.5. Okay, the first A1, the first decimal expansion I have written. Whereas when x equal to 1 by 3, I'll write the first decimal expansion as 3. And for x equal to 751.751, I'll write it 0.7. Have you understood? Now, how do I turn this into analysis? Okay, right. So that the way to do that is the following. Let us look at. See what are the nodes? Nodes are of the form 0 by 10, 1 by 10, and 9 by 10. Right. Therefore, call this as A. This has to lie between 0 and 9. So this is of the form A by 10. Right. So what I am looking for? I look for an x so that x lies in the interval A by 10 and A plus 1 by 10. Then my first I will write it as point A1 where my A1 is A. And dot 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 dot. Is it okay? Right. Now how do I find this? So what do? You look at, so what is the A1? A1 is the largest A in 0 to 9 so that x is greater than or equal to A by 10. That's it. For example, take x equal to half, then okay, half is greater than 0 by 10, 2 by 10, 3 by 10, 4 by 10, 5 by 10, and that's the largest. 6 by 10 it is not. And similarly 1 by 3, the largest is 1 by 3 is greater than 3 by 10 but less than 4 by 10. Follow that? Therefore what do I have? Therefore I have found my x lies in the interval, and notice that since the largest, therefore what do I know about x and a plus 1 by 10? This will be strict. Are you following? Therefore what I have found? I have found my x to be a by 10 then or equal to x less than a plus 1 by 10. Have you understood? So pause. Okay, what is the next step? Next step is, suppose my x lies in the interval a by 10, a plus 1 by 10 open, right? Then what do? I break this into 10 subintervals of equal length. What does that mean? Okay. So what is the total length? Length of the interval is 1 by 10. That means I have to break it into length of subintervals of length 10 squared. Therefore, what will I do? So I will have something like, let me again write it. This is my a by 10 and this is a plus 1 by 10, right? Included, and this is open. Then this I can write as 10a by 10 squared. Therefore, this will be next one. Are you following? 10a plus 1 by 10 squared, and this is 10a plus 9 by 10 squared. This is 10a plus 10 squared. Okay. Are you following? Just let us look at a very concrete example, right? Let me look at my x equal to 0.75. So I knew it, right? Then trouble this. Then what do? This I write it as 70 by 10 squared, and this 80 by 10 squared. Then what will I have? This will be 71 by 10 squared and 72 by 10 squared and so on. And this will be 79 by 10 squared. Are you following? Yeah. Now, what do I do now? So I know x lies in the interval 7 by 10 to 8 by 10. Now this interval is again broken into, partitioned into 10 subintervals of equal length. Therefore, I look for where x equal to 0.751 lies. Where does it lie? Naturally, it lies here. Where does it lie? I'll just write it. This is going to be 75 by 10 squared and 76 by 10 squared. So, my x lies here. Okay. Therefore, I choose my A2 to be 5 because that's the fifth interval. This is okay. This is what? This is 10a plus 5 by 10 squared. A is 10 now. That is your A1. Okay. That is 10, 7. Therefore, 70 plus 5, 75. Are you following? Sure. Okay. So where do you think 1 by 3? What will be my? So I already found it is 3. What will be my A2? A2 again is the same thing. So I have 3 by 10 or 30 by 10 squared, and this is 40 by 10 squared. Therefore, I should look for 33 by 10 squared and 34 by 10 squared. Therefore, my x lies somewhere. Yeah. Therefore, my A2 is also 3. Therefore, it becomes 0, 3, 3. I hope all of you get it. Yeah. Now, let's go back to our half. So, there I found out it lies in 5 by 10, and that is 50 by 10 squared, and this is 51 by 10 squared. Therefore, this will be 60 by 10 squared, 51 by 10 squared, and so on. Right? Now, where does my half lie? Half lies only here. Therefore, my A1 was 5, whereas A2 was 0, because it lies here. Right? This is 10A1 plus 0 by 10 squared. So, it lies in this interval. Okay? So, how do you think I will define A2 analytically? So, given x in the interval 0, 1, how am I going to define A2? A2 I am going to define as the largest A in 0, 1 to 9. So that what happens? So I already had x, right? What do I want? I already found out A1 by 10, right? Follow that. Okay. Right. So what do I want? Largest A with what property? Greater than or equal to A by 10 squared. That is, x is greater than or equal to A by 10 plus A1 by 10 by A by 10 squared. That is the largest. Make sure you understand that. Okay. I understood this trick. So what have we been doing? What have we been doing? At each time, okay, look at x, where does it lie in the subinterval? Then take that subinterval, divide it into 10 equal parts. In the sense that 10 subintervals of equal length. Okay, then locate it. This is the geometry. Analytically, how will I do? Like this. So let me just look at, so how to define an. Suppose I define a1 up to an minus 1. Okay, therefore I have written 0.a1, a2, an minus 1. But what does this really stand for? Let us look at this. A1 by 10, a2 by 10 squared, plus an minus 1 by 10 to the power n minus 1. Right? So my x is greater than or equal to this, but this is strictly less than this one. A1 by 10 plus an minus 1 by 10 to the power minus n, an minus 1 plus 1 by 10 to the power plus 1. So remove it. Okay, are you following? It's greater than or equal to, that is a1 by 10 plus a 10 squared plus a n minus 1 by 10 to the minus 1 than or equal to x. And this, but then it's strictly less than, you write everything up to this, a1 by 10 plus a n minus 2 by 10 to the minus 2 plus a n minus 1 plus 1 by 10 to the power n minus 1. Are you following? Yeah. So you are looking for the largest a, so that it lies in a by 10 to the power n minus 1 and less than a plus 1 by 10 to the power n minus 1. That's what we are looking for. The largest a, so that x lies somewhere here. That's what we found. I understood? Yes? Very good. So what do you think I would do? I have done. Okay. So for example, for 0.753 or I don't remember, 7.1, I do that. Yeah, 7.1. So what will happen to this? This will happen as, okay, my A1 7, A2 5, A3 will be 3 and A4 will be 0 and so on. Yeah, right. So let me summarize. Okay. X is in the interval 0 1. Okay. Choose A1 an, that what happens, a1 by 10, 2 by 10 squared plus an by 10 to the power n is not equal to x, less than a1 by 10 plus an minus 1 by 10 to the minus 1 plus an plus 1 by 10 to the strict. Right? Understood? Therefore, where does x lie? Right? Therefore, notice that x minus summation ak k equal to 1 to n, okay, is strictly less than 1 by 10 to the. Are you following? Because it lies in here, an by 10 to the power n, an plus 1 is not a n plus 1. Wrong. An plus 1, that is 1 plus an by 10 to the power. My x has to lie here, right? Therefore, what is it? Okay, x is greater than or equal to this. Therefore, x minus this will be at most the length of the interval. That is the distance between x and this will be less than or equal to distance between an plus 1 by 10 to the power n minus an by 10 to the power, which is 1 by 10 to the power. You understand this? Okay, have you understood? Very good. Now do you see that we got a decimal expansion of a decimal expansion of x? How? Really? So this I have done for each and every n. Therefore, let me write this. Therefore, my x I claim is this, a n by 10 to the power n, n running from 1 to infinity, which, as you know, I usually don't want to write n greater than or equal to. Okay, what is the meaning of this? Remember, where does my where do my ANs lie? They lie always in 0 to n, 0 to 9. Okay, and therefore this is a series of non-negative terms. Okay, right. Next thing, do I know this series is by conversion? N by 10 to the power n. Is it conversion? Yes. Why? Again, I do comparison. Each an is less than or equal to 9 for all n. Right? Therefore, let me look at the series 9 by 10 to the power n equal to greater than or equal to 1. Is clear? Is that clear? Therefore, I can take 9 this. Therefore, it will be 1 by 10 to the power n, where n is greater than or equal to 0. But this is a converging geometric series, so that 1 by 10, 9 by 10 to 10 by 9, which is right. Therefore, this series is convergent and the sum is 1. Right? Therefore, by comparison test, I know this series an by 10 to the power n greater than or equal to 1 is convergent. Okay, these are all non-negative terms. Right? So I know the series is convergent. Therefore, okay, the sum of the series is a real number. Okay, I claim the real number is x. That is, x is this. Okay. Why is that? Because what is the partial sums of the series Sn? That is going to be a1 by 10 plus an by 10 to the power n. Right? Now, what is x minus Sn? That we saw is less than this is a, okay, we know that this is less than or equal to x, but x is less than Sn plus 1 by 10 to the power. Right? Because an plus 1 by 10 to the power n, therefore it is Sn plus, follow that. Therefore, it is less than or equal to 1 by 10 to the power n. Yeah? Now, therefore, by sandwich lemma, this is a constant sequence is converges to 0. This converges to 0. Therefore, Sn converges to x. That means, okay, the sum of this infinite series an by 10 to the power n is this is called the decimal expansion. And usually you won't write it as a1, a2, an and dot dot dot, but actual meaning of this decimal expansion, now I'm sure you understood what does it stand for. When I write x equal to this, it actually stands for its series. Okay, have you understood? Yeah, you have followed that. Now there is a tricky question. Okay, we had already proved the existence of a decimal expansion for a real number x, which lies in the open interval 0, 1. Right? Again, but all of you know, when I write half, I can write in two different ways, 0.5, or you have to do it, but it's very easy, 0.49999, add in, keep on doing it. Okay, what does that stands for? That stands for 4 by 10 plus 9 by 10 squared plus 9 by 10 cubed plus so on so on. That means 4 by 10 plus summation 9 by 10 to the power k, where k is greater than or equal to 2. This infinite series, if you add, you will find it is exactly half again. So there are two different decimal expansion, right? Now the way we constructed, we will say it's unique. That is, for example, half, our decimal expansion will be only 0.5. It will not be 0.4999. Okay, the recurring decimal expansion will not occur in our this kind of recurring. Okay, that we will prove next. Yeah, let us now prove an important observation about the expansion that will allow us to prove weakness of decimal expansion of a specific kind. So let us start with x. Let's assume that it is same as saying a. Now x is where? X 1. And what do I know about an? An lies in 9, right? And with what kind of property? That is a by 10. An by 10 is not equal to x and larger than a1 by 10 an minus 1 plus an plus 1 by 10 strict. It is a property was shown, right? Now what I want to claim is that for every n, a natural number, there exists an integer k greater than n, that my ak is not equal to 9. Understand this? So let's just look at it this way. Standard way of writing expansion, you are given, then I know there is an ak. This ak is not equal to, okay? So for any such n, I should be able to find one. So in particular, okay, you know that after certain stage 999 cannot keep occurring. Understand that? So like this cannot happen. The popular way of writing will be an 9 bar. After this cannot happen. Now how do I prove that? So let n be the first there, that a k to 9 for all k greater than, right? That is, there exists some integer n, so that after starting from an, every ak, the kth decimal coefficient is, right? Now let us see what happens. Therefore let me write ax a1 by 10 plus an minus by 10 to the, maybe I will write a k plus 1 an by 10 to the power, right? Plus then what happens? 9 by 10 to the power n plus 1 plus 9 by 10 to the plus 2, right? All ak for k greater than or equal to n plus 1 is 9. Now you know what is going to happen, right? This you can take 9 10 to the power n plus 1 outside, then this is going to be equation, okay, 1 by 10 to the k greater than or equal to 0. You agree with that? But this is a geometric series. Where does it converge to? I know it converges to 1 by 1 minus 1 by 10. Therefore, whole thing is the power n plus 1 and 10 by 9, that is 1 by 10 to the. You accept it? Therefore, what do I have? I have x equal a1 by 10 plus an by 10 plus 1 by 10 to the power n, which is same as saying a1 by 10 plus an minus 1 plus an plus 1 by 10 to the, yeah, but that's a contradiction. Why? Saw that my x for chose an such that this inequality should happen. So in particular, the last inequality should be strict. That is being violated. Yeah. So what have you proved? So we have proved our construction of expansion such that for all n natural number, there is a k greater than n such that ak is not 9. Okay, pause. Right. Now we are ready for the final result. Now we had already proved the existence of decimal expansion, and I also made an observation about the decimal expansion. Okay, 999 cannot keep occurring not infinitely, completely. After certain stage, the entire tail is of ANs are 999. That cannot happen, right? Okay. Now let us look at this one, right? So let us look at functions. Call it d or delta. The function from the set of natural numbers, set of digits 1 up to, maybe call it a alpha, right? This function, it takes values only 0 to 9. Then for each function I can associate a decimal expansion, namely let me let an be alpha at n. I can associate it to an by 10 to the power n and n greater than equal, right? We already know this is convergent, right? And what do we know? We also know ans are greater than equal to 0. Therefore an by 10 to the power n, this is a non-negative series, and this will be less than or equal to 9 by 10 to the power n, and therefore it is 1. Therefore this is a number, this sum lies between 0 and 1. Okay, right. Now I don't want to take all such alpha. Remember, when any alpha, a function from natural numbers to 0 to 9, I associated decimal expansion, a power series, not sorry, an infinite series, right? That represents a number in post interval 0. But what do I want? I want it to be in the open interval 0. Okay, so what should I make sure? I want to make sure that not all ANs are, there exists an n, that AN is not. That's the first assumption. Then I would like to say it has to be 0 close to 1. And this one also I want to say it cannot happen. Why? Because it has to happen, what should happen? So this must be, only way it can happen is 9 10 to the power n. This will be 1. But what do I so what do I have to make sure? Alpha is said that if alpha n equal to 9 for all n, then I will get 1. But I don't want 1. So what condition should I impose? Exactly the condition which we just now saw. Assume that alpha satisfies, okay, that is n, there exists k greater than n, that alpha at k not equal to 9. Okay, therefore alpha goes to summation an by 10 to the power n, n greater than equal to 1. At least there exists at least one n, that an is not equal to 9, right? Very good. Then I claim this has to be less than 1. That is, and also we are assuming there is an answer that n is not equal to 0. Therefore I want to say this unit series, it's a sum lies strictly between 0 and 1. We already made sure it is greater than 0, and I want to make sure it's also less than 1. This follows very beautiful facts from convergence of positive number, non-negative number. So let us make simple observation. See, these are the things you will know why learning infinite series, the theoretical background is important. Otherwise you think it's like algebra, you manipulate symbols. Okay, when somebody points out something, then you are at a loss, you may not be able to. Let me explain. So let us assume an and bn's are non-negative, and let's assume an is less than or equal to b, right? And assume further, okay, there exists n so that an is, okay, n is greater than or equal to b. an is strictly greater than b. At least one n that an is strictly greater than b, right? And further assume the infinite series an and the infinite series bn are convergent. Notice that if I know this is convergent, by comparison test, this will also be convergent. That will be automatic, right? Now I'm sorry to use the same symbol alpha. Okay, let s equal to the sum of the series, let t equal to the sum of the series, right? Then what do I know? I know that Sn is always less than or equal to Tn for all n, and since this is a series of non-negative terms, its a sum t is nothing other than LEB of Tn's. Therefore, this is less than or equal to t. Therefore, Sn is less than or equal to t. Therefore, t is an upper bound for Sn. Therefore, S, which is the LEB of Sn, is less than or equal to t. So, we know S is less than or equal to t, right? What I want to claim is S is strictly less than t. That's because at one place an is strictly greater than b. Otherwise, an I know only is greater than or equal to b. That's it I know. You understand this? Isn't it the thing? It's a finite sum. I know you can immediately prove it. For example, if it's a finite sum, how will I do? A1 minus b1 plus an minus bn. Suppose. Okay, suppose this is strictly greater than 0, this is greater than or equal to 0. Then I know this is that's easy. But the same logic is what we are going to use, except we have to use the theory of convergence series and also the fact we are dealing with non-negative terms, series of non-negative terms. It's a very beautiful thing. So what do I want to prove? I want to prove S is strictly greater than t. Let's look at S minus t. Now what is S? S is sum of this infinite series. What is t? Sum of the infinite series. And remember, yes, these are all convergence series. Therefore, what do I know? This series an minus bn is convergent and its sum is S minus t. Okay, this is algebra of convergence. You understand this? Very good. Now, what do I know about the series? This series, since an is greater than or equal to 0, greater than or equal to bn, an is greater than or equal to 0. Therefore, this is a series of non-negative terms. Right? So, let un be the partial sums. Summation an minus bn. Right? Okay. Then what do I know about un? Un is a1 minus b1 plus an minus bn, and these are all greater than or equal to 0. But this is strictly positive, therefore this is strictly positive. You understand this? Okay. Therefore, capital N is strictly positive. This is more than enough now. Now, where do un converge? Un converge S minus t, because this series is convergent to S series, that is Sn, and that converges to S. This series Bn, partial sums are Tn, that converges to T. Therefore, this minus this is nothing other than this series An minus Bn. Okay, that converges S minus T. You understand that? Right. But what do I know about the series? The series an minus bn is non-negative, series of non-negative terms. Therefore, what is the sum? Sum is limit un is the least upper bound of un's. You understand? But remember, since I know limit un is s minus t because algebra convergence series, but I know this LUB must be greater than or equal to un, but that particular un is already positive. Therefore, I get s minus t. That means, see that? It's a very easy fact how much of theory we needed. We needed various things. I needed series of non-negative terms, converges, then it is not, the sum is the you have the partial sums. That fact I needed, and used comparison test. I also used the algebra convergence series. cos z2. Now let's complete the proof. Okay, this is the crucial I said. I hope all of you loved this. Okay, it's non-trivial, but people usually slur over such things, say it's obvious, but it's not. Now, what is our thing? Alpha set of function from this to 0 to 9 with what property? 1, or there exists a k so that alpha k is not equal to 0, and 2, for every natural number n there exists a k greater than n so that alpha k is not equal to 9, right? Then let us look at where does alpha go to. Alpha goes to alpha n by 10 to the power n, which is same as a n by 10 to the power n, right? Now notice that my a n's are all less than or equal to 9, and since alpha satisfies the second condition, there is at least one k so that all a k is not 9. Therefore, a k is strictly less than 9, right? Therefore, there is a k so that a k is strictly less than 9. So, what do I know about this? So, this a n by 10 to the power n is less than or equal to 9 by 10 to the power n, which is 1, right? Therefore, this strict inequality should hold because a k is strictly less than 9 by whatever just now I said. Therefore, what I have shown now, therefore alpha, okay, goes to the decimal expansion, namely summation a n by 10 to the power n, n greater than or equal to 1 is, okay, lies in open interval 0, 1. It's not 0, it's not 1. Okay, next I claim that's also 1, 1. So call this as phi of alpha is the decimal expansion a n by 10 to the power n, n greater than or equal to, right? Therefore phi, next one is phi is 1, 1. That means if you give me an alpha and beta satisfying those conditions, if alpha is not equal to beta, what does it mean? That means there is at least n, 1n, n, that alpha at n is not equal to beta of n. Let me call it an and bn, right? Then I want to say phi of alpha is not equal to phi of beta. That means an by 10 to the power n is not equal to by 10 to the power n. Okay, right? But that's very easy because let n be the first integer so that an is not equal to b. So without loss of generality, I can assume an strictly greater than b, right? Now let's look at what is phi of alpha minus phi of beta. That is going to be an by 10 to the power n minus n by 10 to the power n. These are the numbers in the interval 0, 1 down to 0, right? And these are all convergent. Therefore, by algebra convergence sequence is an minus bn by 10 to the power n. So what do I want to prove? I want to prove this is actually strictly positive. If I prove that's positive, then I am through. What is the assumption? I am assuming alpha is not equal to beta. That means there is an n so that an is not equal to bn. So let us assume there is a capital N so that an is not equal to bn. So loss of generality, let me assume an is strictly greater than bn. Then I want to say phi of alpha is strictly greater than phi of beta. Okay. Therefore, this is very easy. Okay. So this is the first n, right? Therefore, up to this is going to be what? So n, okay, k greater than or equal to n of ak minus bk by 10 to the power n. Right? K is greater than or equal to n. Do all of you agree with that? Yes? Now, something very interesting happens. Now, what are AKs? AK right in 0 to 9, and bk is also lie there. Therefore ak minus bk, okay, that will be greater than or equal to minus 9. Is it okay? And are you following? Worst possible scenario for ak is 0. Worst possible scenario for bk is 9. Therefore ak minus bk will be greater than or equal to 9. Right? Therefore this fellow is equal to, right? But that the first thing is an minus bn by 10 to the power n plus summation ak minus bk by 10 to the k, where k is greater than or equal to n plus 1. All of you agree with that? Yeah? But therefore this is greater than or equal to, now remember a and bn's are all integers. Therefore an minus bn will be greater than or equal to 1, because an is strictly greater than bn. Right? Therefore this will be 1, whereas this will be greater than or equal to 9 by 10 to the power k, k is 1. Right? And that's positive. Right? It's exactly similar to the earlier proof. Right? Okay, so what do you think I have proved? So let me summarize. This is the theorem you have proved. Let A be collection of all functions from 0 to 9 such that 1, there exists m such that alpha at m, that is am, not equal to 0. 2, for all n k greater than n such that alpha k is not equal to 9. Okay, then consider the map. Let phi be the map from A to open interval 0 1 given by alpha going to equation an by 10 to the power n greater than 1, where a, that means first claim is phi of alpha maps into open interval 0 1, and if alpha is not equal to beta, phi of alpha is not equal to beta, therefore it's 1 1, and we had already seen it's on 2. We also phi is on 2, that is given any x in 0 1, I have an, okay, in 0 n, so that x is summation an by 10 to the power n, and so that this an satisfy the conditions, namely alpha. If you think of alpha as an, then alpha belongs to our set A, that we had already seen. This completes. Now just suppose I want to look at binary or ternary expansion. What do you think I will do? Take the same thing 0 1 and make it 0 half half and 1. Or if ternary, this is binary. For ternary, 1 by 3, 1 by 3 to 2 by 3, and 2 by 3, 3 by 3, which is 1. Okay, and get x here, then again is divided into subintervals of equal length, namely 1 by 3 squared. Here it will be 1 by 2 squared, and so on. And therefore you know how to write down the conditions also. Okay, how will I choose my ak? Ak in the first case, binary case, ak lies in 0 and 1, and in ternary case, ak will lie between 0 1 and 2. Okay, and I stop here. The details about binary and ternary etc. are exactly similar. The best way is master the decimal expansion. Then you should feel confident to binary and ternary on your own. In case you get stuck, you can always look into my article. I hope all of you enjoyed. Take care. Stay safe.